I've been thinking this for so long to solve this question paper. So finally today I've decided. Long, but I'm here today. NEPKIT 2026 Civil Engineering paper called PGC. These are some instructions you can read. So question number 1, 200 carries, 1 marks each. And the very first question is, in the limit state method of reinforced concrete design, the depth of center of compressive force from the extreme fiber in compression is, where x is the depth of neutral axis. This is the solution. This comes under the limit state collapse fracture, IS 456 2000 clause 38. It comes under the assumptions of the limit state of collapse. So here you can see that it's clearly mentioned from top to here. This is the center of the XU. This is top portion is compression, and this bottom portion is my tension. So from very top to here, it's 0.42 XU. If you would like, you can refer this. Neutral axis XU is total compression equals to total tension. Total compression is 0.36 FCK XUB. Total tension is 0.87 FYST. So from here, XU is 0.87 FYST. B for balance section, you can see that this is my compression, this is my tension, this for the strain, this for the stress. Here to here it's XU. So this is going to be my D minus XU, because this total is my D, and this is the center of the compression. This would be my compression. You can see that. So this is going to be the D minus 0.42 XU. You can refer this if you'd like again. Now let's move to the question number 2. The shape vector of a circular section is, shape vector is given as ZP by ZE. I have wrote down here, as you can see. So first of all, we'll find out the value of ZE, and then after that we'll find out the value of ZP. ZE is equals to I is moment of inertia divided by Y max is equals to, for what is this? For a circular section, for I, we know that it's pi d to the power 4 divided by 64. And for Y max, it's d by 2. When we solve this, after cancelling out, we are left with pi d cubed divided by 32. And now we need to solve for ZP. ZP is equals to A, area divided by 2, Y1 bar plus Y2 bar equals to, we know that for a circular area, total area is pi d squared by 4. So if it's half semicircle, then it's going to be pi d squared by 8. So after that, what we need to do is, we know that for a semicircle, it's 4r divided by 3 pi is equals to, for r we can write the radius, we can write d by 2, 3 is going to remain same, it's going to 2d by 3 pi. And for ZP, now we'll substitute the value. For ZP is area is pi d squared by 8, and for Y bar is 2d by 3 pi plus Y2 bar is also going to be same 2d by 3 pi. After solving this, we're gonna get d cubed by 6. Now S is equals to ZP by ZE. ZP, the value of ZE is my d by d. The value of ZP is d by 6, and the value of ZE is pi d squared. After solving this, we'll get 16 divided by 3 pi. When we put this in a calci, then you'll get 1.7. Okay, for a third problem, for a rectangular section of the wood B and a depth D, the plastic section moduli about the major and the minor axis is BD squared by 4 and DB squared by 4 respectively. The spacing of the vertical stirrups in a rectangular beam is vertical stirrups. It resists the shear force in simply supported beam. And we know that the shear force is maximum at the support and the minimum at the center. So basically we'll provide the stirrups closely at the end, where the shear force is maximum. We'll provide the stirrups at that place, that means in the corner, and farther we'll move towards in the middle. So it's increased at the center of the beam. It will increase at the center of the beam. And for this, the unsupported length of the compression member in L, effective length of the compression member when the translation and the rotation at the end are restrained, and at the other end only the translation is restrained is. So basically the question has asked about this one, effectively held in position at the both end, restraints against the rotation at the one end. So for this would be hinged, and this is going to be my fixed, so it's going to be 0.8 L, and for the theoretical value it's going to be 0.7. And these are 1, 2, 3, 4, 7. You need to remember this every time they ask 1 marks question from this table, and club this table in your mind. And for question number 6, a beam AB is fixed at the both end and carries a uniformly distributed load of intensity W per unit length to run over its entire length. Due to some constructional defect, the end B is now reduced to simple support. The percentage increase in the bending moment at the end is written here. As you can see that the both end fixed for the initial value for the simply supported beam. Maximum bending moment will be W squared by 12, and for the final it's going to be W squared by 8 final. So in percentage increase in the bending moment is going to be my final minus initial bending moment. W squared by 8 minus W squared by 12 is going to be my W squared by 24. So now you need W squared by 24 divided by W squared by 12 into 100% is equal to it's going to be my 12 and 24 into 100 is going to be my 50%. Hope you understood it. This W and this W will get cancelled out. This will move to upwards numerator, and this is going to move to the denominator. Then 12, 24 into 100, it's 50%. So answer is my 50%. Now let's move on to question number 7. The maximum strain in concrete at the outermost compression fiber in the limit state design of collapse in a flexural IRC 456-2000 is, I think here it should be IS, not IRC. Yeah, IS 456-2000 is 0.0035 for this. This is also from the assumption, as you can see here, that the maximum strain in a complete concrete at the outermost compression fiber is taken at 0.0035 in the bending. How it came, all of these things I cannot explain you. It will be very expansion of the video, so just remember this. And the next question number 8, is the minimum shear reinforcement in a rectangular beam shall be provided when for this design of shear reinforcement. You can see it is provided. You can see that when the tau V is more than the tau C, shear reinforcement is to be designed and can be provided in the following form: vertical stirrups or in the bent up bars along with the stirrups. Tau V is my nominal shear stress, which is given by tau V equals to VU by VT. This is my shear stress. Tau C is my shear strength of concrete, or design shear strength of concrete. As you can see here, it is clearly mentioned. When our tau V is greater than tau C, we need to provide the shear reinforcement as a vertical stirrup or bent up bars. These are the steps for the designs. And for a grade of concrete, tau max, if it's M15, M20, M25, 30, you need to remember this tau max Newton per mm square. For M15 is 2.5, M20 it's 2.8. Basically, sometimes it is asked for this M20 2.8. Just remember this or see each of them. Question number 9. The ratio of bone stress for the deformed bars in a compression to plane bars in a tension is for HYST or TMT bar design bone stress increases by 60%, factor will be 1.6. For the bars in a compression, it's 25% increased by 25%, factor will be 1.25%. So therefore the total compressed to the plane bars in a tension is going to be this 1.6 into 1.25 is basically 2.0. So this would be our answer. As per the limit state method of the reinforced concrete design, the vertical limit deflection, it is my 26. What it is, span to effective depth. It is my, I can show you the, here it is, IS 456-2000, page number 37. You can see here for the span to the depth ratio for cantilever it is 7, simply supported beam it's 20, for continuous it is 26. So here it is asked for the continuous beam, it's going to be 26. And for Muller's Bruce principle in a structural analysis is used for drawing an influence line diagram for any force response in the structures. And a 3-hinge arch is for 3-hinge arch. This is my internal hinge. Here the bending moment is equal to 0, because of which one reaction will generate. So here it's my HA. For the hinge support, we know that BA and HA, BB, HB. So here we have two reaction, none, and here we have one. And we know the degree of indetermination is R minus R. This R is my number of support reaction. This R is my number of equilibrium. We know that for equilibrium, summation f of x equals to 0, summation f of y equals to 0, summation mz equals to 0. For this internal hinge, there will be one extra will be generated. So therefore, we have like 4 number of equilibrium. So therefore this R number of support reaction is 1. Here we have 1 and we have 2. 4 minus 4, it's going to be a 0. These are my notes for your reference if you need. Everything is written in a clear manner. Please refer it. So for this, it's going to be my statically determinate structure. And the maximum bending moment due to moving load on a simply supported beam occurs under the load. It's given by N equal to WAB divided by L. Principle of superposition is valid when the stress-strain relationship for the structural material follows Hooke's law. It's time for question number 15. Maximum bending moment in a simply supported beam occurs in the position where we know that shear force, this is the shear force diagram and this is the bending moment diagram. The maximum bending moment in the simply support occurs where the shear force is 0. So you can see that here the shear force is 0. So here it will be the maximum bending moment will occur. The shape of the most commonly designed highway vertical curve is parabolic. A highway designed for a speed of 100 km per hour has a horizontal curve section with a radius of 500 meter. If no super elevation is provided, the required coefficient of friction is, know that E plus F plus V squared by GR, or if you want to write it in direct kilometer per hour, it's going to E plus F equal to V squared by 127 R. Here it is. So we consider this E equals to 0, then you can substitute these values in this formula and you'll get 0.16. V square is my 100 square divided by then 127 into 100 radius. It's 0.157, so we can opt as a 0.16. And for the next question number 18, the capacity of the jam density of the stream are 1800 vehicle per hour and 100 vehicle per kilometer respectively. The average time headway and the distance headway, average time gap and the distance gap between consecutive vehicle respectively are, you know that space time headway is 3600 divided by capacity. So 3600 divided by capacity is my 1800 vehicle per hour. So it's going to be 2 seconds. And for space headway, HD is equals to 1000 divided by jam density. Jam density is 100 vehicle per kilometer. So 1000 divided by 100, it's going to be 10 meter. So our answer is going to be 2 seconds and 10 meter. The test designed to evaluate the toughness of this stone is impact. The severe test, the value of the severe is calculated about 2.5 meter mm and 5.0 mm penetration. I think these things don't need an explanation. These are the terms that you need to remember. I can explain it, but it will be very lengthy. On a horizontal curve, if the pavement is kept horizontal across the alignment, then the pressure on the outer wheel will be more than the pressure on the inner wheels. As you can see that this is the road. This is in a longitudinal direction. It says that across. It's written somewhere that it's across. The vehicle is placed across the road. This is my inner wheel. This would be my outer wheel. Centripetal force will try to move the vehicle outward, whereas for the centripetal force will, or CG of the vehicle will try to move the vehicle inward. But in both ways, it should be in such a way that it should equilibrium each other. So pressure in the inner wheel will be low, and the pressure in the high outer wheel will be high. Also, these are the notes that if you would like, then you can refer it. Everything is written here.